You are welcome to this class. Well, today's topic is distribution of magnetic nuclei in various spin states in the presence of an external magnetic field. So, we may also call it relative distribution of magnetic nuclei in various magnetic quantum states. Well, by now we know that the spin quantum number of hydrogen nucleus or hydrogen type nuclei that is I is equal to 1 by 2. Therefore, such nuclei have two spin states available to them. They are given by their Mi values. Mi value can be plus 1 by 2 or Mi value can be minus 1 by 2. So there are two spin states available to such nuclei, and in the absence of any magnetic field, the spin states corresponding to Mi value plus 1 by 2 as well as Mi value minus 1 by 2, they are of the same energy. So we say that the two magnetic quantum states corresponding to Mi value plus 1 by 2 and Mi value minus 1 by 2, they are degenerate. Now we can show that on an energy level diagram like this. So this is energy, and in the absence of any external magnetic field, both these two states have the same energy, and we can show arbitrarily this energy level here with respect to some origin. So this is the energy level for the quantum state Mi value plus 1 by 2 and Mi value minus 1 by 2. Now when we have a sample, for example, we have a sample of organic molecules, and in a sample there will be millions of hydrogen nuclei or protons, and since the two states are of the same energy, on an average the two energy levels will be equally populated. So for example, if the sample has 2 million protons, so the 1 million protons will have a spin state corresponding to Mi value plus 1 by 2, and 1 million protons will be having a spin state corresponding to Mi value minus 1 by 2. But as we know that, so this was where there was no field, we can put it here as H naught, that is the external magnetic field, is equal to 0. So what happens when we put the sample in an NMR instrument and apply the external magnetic field. So when we apply the external magnetic field, the degeneracy of these two spin states is lifted, and the energy of one spin state corresponding to mi value plus 1 by 2, it decreases with increasing the magnitude of the applied field. And in the same way, the spin state corresponding to mi value minus 1 by 2, its energy will increase and it will rise in energy. This is mi value corresponding to minus 1 by 2. The energy of this state, this spin state, it will be equal to minus gamma h bar h naught divided by 2, because its mi value is plus 1 by 2, so the overall energy expression will be minus gamma h bar h naught divided by 2. And in the same way, the energy for this state, that is when mi value is minus 1 by 2, the energy will be equal to gamma h bar h naught divided by 2. So this is the lower energy and this is the higher energy. And the difference between the energy difference between the two states, that is this difference, and this energy difference, that is delta E, this delta E will be equal to gamma h bar h naught. So this is the difference between the difference of energy between the two nuclear spin states. So when there was no applied field, when the applied field was equal to 0, all the hydrogen nuclei, or simply protons, they will equally distribute between the two states. So for example, if there are 2 million hydrogen nuclei in the sample, 1 million will occupy the energy spin state corresponding to mi value plus 1 by 2, and 1 million will occupy the state corresponding to mi value minus 1 by 2. But as soon we put the applied field, so this is the applied field, with increasing the applied field, there is the degeneracy of the state is lifted and the energy level, energy of the two states, it begin to differ. The energy of the one state will decrease, the energy of other state will increase, and that difference will be proportional to the field strength. Now in such a case, what will be the population of two states? One state with mi value plus 1 by 2, we may call it alpha state, and mi value minus 1 by 2, we can call it beta state. So this one is the ground state, this is the alpha state, and this one, this is the beta state. So now today's talk is precisely about the distribution of magnetic nuclei between these two states, between alpha state and between beta state, and how we can get that distribution, how we can get the relative distribution of the particles of the magnetic nuclei belonging to different quantum states. For that we invoke Boltzmann distribution law. So this is the law which gives us the distribution of particles in two different energy states having different energies, and that law will be that number of nuclei, number of magnetic nuclei occupying the beta state, that is the excited state, higher energy state, to the number of particles or the number of protons here having the energy corresponding to alpha state. That relative population of the two states, it will be given by exponential minus delta E by kT. What is delta E? Delta E is the energy difference between the two quantum states, two magnetic quantum states, and K is the Boltzmann's constant, T is the temperature. Now what is the energy difference between these two states? the energy difference we can take here, and we can write it is minus, then it is gamma h bar h naught divided by kT. So this is the exponential raised to power minus gamma h bar h naught by kT, or I can write it here like this. So the population ratio between the two states, it is given by exponential minus gamma, h bar is h by 2 pi, so I write here h, this is the magnetic field, magnitude of the magnetic field, divided by 2 pi kT. Now where gamma is the gyromagnetic ratio, h is Planck's constant, h naught is the magnitude of the applied field, and K is Boltzmann's distribution law, and T is temperature in Kelvin. So first of all, I write the values of these constants. So this is the expression. Here we can use this expression to determine the relative population of the two states, two nuclear simple states. That means how many particles will have energy corresponding to mi value plus 1 by 2 state, and how many particles in a sample will have the energy corresponding to the state designated by mi value minus 1 by 2 in the presence of an electromagnetic field. So the values for these constants is, so the gamma value for hydrogen nucleus, that is hydrogen nucleus, the gamma value is 2.68 into 10 raised to power 8 radian per Tesla per second. The next Planck's constant, we know the value is 6.63 into 10 raised to power minus 34 joule second, and the Boltzmann's distribution, Boltzmann's constant K value, it is 1.380 into 10 raised to power minus 23 joules per Kelvin for molecule. Now using this expression we can calculate, and let's take an example and to see that what will be on an average, what will be the distribution of the population between these two states. Why is that important? Because if we assume, for example, that the population between these two states is the same, then if the population is the same and we expose it to electromagnetic radiation in the radio frequency region, that is, we expose it to, we irradiate the sample or expose the sample to radio frequency radiations, then the population different, if the population ratio is same, some of the particles in the ground state, they will absorb the radio frequency and they will be excited to the excited state. Then the probability of that is same, that some particles in the excited state emitting the photon, radio photon, and returning back to the ground state. So if the population in the two states is same, then we call that will be a state, while the absorption probability will be same as the emission probability, and there will be no net signal will die down, and that state we call a saturation state. So then that means in that sense we are not able to record the NMR signal. So that means there must be some population difference, and let's see what can be on average, what that population difference can be. So we can take an example and solve that problem and see what is the population difference between these two states. Now, for example, what we do, we will calculate the relative number of protons in the two quantum states, higher magnetic quantum state and lower magnetic quantum state, when a sample is placed in a 4.9 Tesla magnetic field at say 293 Kelvin. That means 20 Celsius. So let's try to do it. So how we do it? We'll use this equation. So that means the number of protons of the sample in the higher state, the ratio of the number of protons in the higher state is beta state to the number of protons in the alpha state, that will be equal to exponential minus, then there will be the delta E by kT, that will be in this case gamma H naught by 2 pi kT. So that will be equal to exponential minus, so gamma, we had the value of gamma, it is 2.68 into 10 raised to power 8 radians per Tesla per second. Then the Planck's constant, it will be 6.63 into 10 raised to power minus 34 joule second. Then we have the magnetic field, so the magnetic field will be 4.9 Tesla, and we divide this by 2 pi kT, so it will be 2 pi into k. K is 1.380 into 10 raised to power minus 23 joules per Kelvin, then into 293 Kelvin. So when you solve it, we do the arithmetics, we will get the ratio equal to n beta by n alpha, that's the relative distribution of protons in two states, that will be equal to exponential minus 3.28 into 10 raised to power minus 5, and that will be equal to 0.999767. So that means if I want to determine the relative number of protons occupying the alpha state, that is the ground state here, to the number of particles occupying the higher state, that means the beta state, that will be n alpha here, it will be equal to n beta divided by 0.99967. Now for example, if we say in these conditions, the condition is that the field is 4.9 Tesla and the temperature is 293 Kelvin. In these conditions, if we have the population in the beta state, that is higher state, and beta, that is equal to 1 million, that is 10 raised to power 6, 1 million protons are in beta state. Now how many are in alpha state? So we write number of protons occupying the alpha state, that will be equal to 10 raised to power 6 divided by 0.99967, and that comes to be, if we solve it, it comes to be equal to 1, 2, 3, 4, 33. That means if we are employing a magnetic field of 4.9 Tesla and we are placing our sample say an organic molecule or any other material we are placing in the NMR instrument, and we are applying 4.9 Tesla field, and we are keeping the temperature 293 in a classical experiment. What we will see is that if on an average beta state has a population of 10 raised to the power 6, that means precisely that 10 raised to the power 6 protons, 1 million protons, they have the energy or they have the spin. They are in a spin state which corresponds to energy level, higher energy level, that's beta state, corresponding to mi value minus 1 by 2. Then in the ground state, what is the number? What will be the number of protons? The number of protons in the ground state will be 1 million plus 33. That means only if the excited state has 1 million protons here, the ground state has only 33 protons in addition to that 1 million. That means the overall excess of protons in the ground state, that is here the alpha state, which we designate with mi value plus 1 by 2, it will be only 33 parts per million. So 33 parts per million ppm. And now we can realize, we can see that whole of this NMR experiment will depend on only these excess 33 protons. So it is a very small excess, and if this excess would have not been there, there would be no net signal, because the number of protons in the ground state, if it is equal to the number of protons in the excited state, then there is the probability of absorption and the probability of emission, that will become same, and there will be no net signal. So this 33 parts per million, it's a very small excess number of protons in the ground state, but whole of the experiment depends on this, and that's why this NMR signal, it is very weak signal, it is not having much intensity. So we depend on this small excess of protons. Now if we change the magnetic field, now we see from this expression here, this expression can also be written as like this, so we can write it and alpha, it is equal to 1 minus gamma h naught by 2 pi kt. Maclaurin series we can invoke. So for example, e raised to power minus x, it is equal to 1 minus x. So we can see here as well as here that the number of particles, the excess number of particles in the ground state, the excess number of particles in the alpha state, it is linearly related with the magnetic field. Here we can see it more clearly. That means the excess number of the value of n alpha, it is linearly related with the magnitude of applied field. In addition to, it depends on the gyromagnetic ratio. That means this distribution of particles, it will be first different in the same conditions using the same field and using the same temperature. It will be different from one type of nuclei to another, one type of nucleus to another type of nucleus. So some type of nuclei will have some value, some type of nuclei will have another value, because the gamma is an intrinsic property of a certain nucleus, and it varies from one type of nucleus to another type of nucleus. Then for the same, if we see for the same type of nuclei, for example hydrogen nuclei, if we are recording hydrogen 1 NMR, then we are only concerned with the hydrogen nuclei. Or carbon 13 NMR, we are concerned with the carbon 13 nuclei. So in that case, the distribution of the particles, it will be, the gamma will be constant, but it will be linearly related. That means the excess of protons in the ground state, on which our experiment depends, it will be linearly dependent on the field. What that means? That means precisely that if we increase the field, the excess number of particles in the alpha state, that increases. So that's why in the beginning there were the small magnetic fields were being used, which correspond to say 60 megahertz in frequency values on frequency scale. But nowadays we are using a very large magnetic fields, the one important aspect of that is that if you increase the field, you are increasing the relative population in the alpha state. More the excess of protons, more the excess of population in the alpha state as compared to the beta state, more will be the intensity of the signal. So when the intensity of the signal increases, so we are making the experiment more efficient. So this is how we overcome this small axis on which our experiment depends. So we can try and we can have different fields, different temperatures, and try to see that what happens to this ratio, what happens to this distribution of particles. So this was about the distribution of magnetic nuclei between various quantum states in the presence of an external field. If there is no external field, then the two states are degenerate and the population ratio between the two states will be same. Thank you very much for watching this video, and continue to watch the future videos regarding this subject and regarding other subjects. Thank you very much.